geometry question involving roots of unity. It is basically a copy of a question which appeared on the specimen paper for our course. They've not said anything like it ever since. But our exam board, the syllabus says we have to be able to solve geometry questions involving roots of unity, and I suppose this one does the job, but it's not straightforward. Part A is difficult and part B is difficult. I'll try to go through it as carefully as I can. So part A, we are first of all told, given that the following is true. Z times Z star, where star is the complex conjugate of Z, is mod Z squared. So we're telling you that fact. This, by the way, is quite easy to prove. So the reason is that if you do Z times Z star, that's the same as X plus YI times X minus YI, Z times Z star. If you expand the brackets, you get X squared. You also get plus 2xy minus 2xy, which cancels out. You get minus I squared y squared. That's the same as plus y squared. And that's obviously the square root of x squared plus y squared in brackets squared. But that's mod Z squared. That's the reason where that comes from. We're asked to prove that if W is any root of unity, this statement holds. So W is a root of unity means W is a solution of W to the N is 1. And I'm going to use that at some stage in my argument. So we're asked to do this, and we're told this formula for kind of the modulus squared. I've got to prove this, but that's what I'm going to do. Start with the left-hand side, mod of W minus 4 squared. I'm going to use this thing here to rewrite that and then hopefully somehow get to the expression on the right-hand side. So according to this rule, mod of W minus 4 in squared is going to be the same as W minus 4 multiplied by the conjugate of W minus 4. Now, what I'd like to do in a minute is to expand this bracket, but at the moment that's difficult because there's a conjugate sign outside the second bracket. However, it is a rule that the conjugate of two complex numbers added or subtracted is the conjugate of the first plus or minus the conjugate of the second. So I can write this as W minus 4 multiplied by W star minus 4 star. The W star is the conjugate of this number W, and 4 star is the conjugate of 4. And I can simplify that further. 4 is a real number. So if you view as 4 as a complex number, it's 4 plus 0i. So its conjugate is going to be 4 minus 0 times I, which is just 4. If you have a number which is real, its conjugate is itself. So this is the same as W minus 4 times W star, take away 4. And now we can expand the brackets. W times W star minus 4W minus 4W star, and then a plus 16. Okay. But then I can rewrite that again. I know that any complex number multiplied by its conjugate is the modulus squared. So this is the same as mod W squared. I'm going to put the plus 16 next to it, and I'm going to take out minus 4 as a factor of this. Now, the reason for doing that is just that I can see the formula I'm looking for as that form. Right, finally, I'm going to use the fact that W is a root of unity. Any number which is a root of unity, which is the root of Z to the N is 1, will have a modulus of 1. So therefore, mod W is 1. So mod W squared is 1 squared, which is also 1. So that's 1 plus 16 minus 4W plus W star, which is 17 minus 4 times W plus W star, as was required in the first part of the question. So that's the first part done. want to pause the video for a second if you haven't written that down. I'm going to delete this. I'm going to rub this out and then have a go at part 2 of this question, which, as I said, that is also non-obvious and quite difficult. So we get a bit of all of this. And now have a go at part B. That's okay. So part B gives us a problem in geometry, I suppose. So part B, we are given a regular pentagon B1, B2, B3, B4, B5. I.e. its vertices, its corners are at the points B1, and B1 we're actually told is the point 1, 0. And then B2, B3, B4. We've also got a point Y with coordinates 4, 0. I want to show the following geometrical fact. Sigma I is 1 to 5, YBI squared is equal to 85. So what I'm going to do is first of all understand what this expression actually really means, just to make sure we're absolutely clear. And then we'll see how we can relate part B to part A. So what this means is this expression we're trying to find the sum of means YB1 squared plus YB2 squared plus dot, dot, dot up to YB5 squared. And YB1 means the distance between Y and B1. So there's my point Y and there's B1. Now what I'm going to do is convert this expression into an expression involving the moduli of complex numbers. Each of these points on the edge of on the pentagon can be represented by a complex number. Because B1 is 1 plus the point 1, 0, B1 is the complex number 1. And because Y is the point 4, 0 on an Argand diagram, Y is the complex number 4. And then I'm going to have other complex numbers at B2 and B3 and so on and so forth. And maybe I should call these complex numbers. I'll call that one W1, W2, W3, W4 and W5. So these are the complex numbers at this point. Now please note that these are the fifth roots of unity. The fifth roots of unity form a regular pentagon on an Argand diagram with centre the origin where the first point is at 1. So these are the fifth roots of unity. Now what I claim is true is this. Let's not do YBR1, let's just do Y to BI. So YBI means the distance between Y and BI. The distance between 2 points is got by subtracting the complex numbers and taking the modulus. So the distance between Y and BI is WI, take away 4, then do the modulus. So on an Argand diagram, the distance between 2 points is the modulus of their distance. So consequently, YBI squared is the modulus of WI minus 4 squared. And this is how you can connect part B to part A. So what I'm trying to get is the sum from I is 1 to 5 of the modulus of WI minus 4 squared. So I've got this expression involving the squares of distances on this diagram. I've rewritten this using in a way that I can try to use the previous parts. And we also know that the WIs, so W1 up to W5, are the fifth roots of unity. So because they are fifth roots of unity, we can use the expression from part A, and I can write this as sum from I is 1 to 5 of 17 minus 4 brackets WI plus WI star. Okay, And now we can do something with that using our knowledge of sigma notation. So this is like 17 added on 5 times. So 17 times 5 minus 4 times the sum from I is 1 to 5 of Wi plus the sum from I is 1 to 5 of Wi star. That's just splitting up into sigma notation. Now, what's this? This is the sum of the roots of unity of a complex number, and that sum is 0. Sum of the roots of unity of 1 is always 0. This is the sum of the conjugates of the roots, which is therefore going to be the complex conjugate of 0, which is also 0. So consequently, this is 85 minus 4 into 0 plus 0, which is 85, as was required to be shown. Now, as I warned you at the start of the question, this is a highly unusual question. There was a question very, very similar to it on the first specimen paper. It's never come up since. There you go. You can turn over the page. So what we need to know about on our course is about use of complex numbers for doing geometry, but there are further geometry problems which you can solve using ideas. I'm not going to go through this page bit here. I'm just going to go through example 4 down below, which is going to illustrate some facts which are stated above, but I'll go through what the key facts are in just a second. So example 4 has 2 parts for it. Can I first of all do part A? So part A says the complex number z, which is minus 2 minus I, is rotated by pi over 2 radians clockwise about the origin. What's the complex number you end up with? So maybe to draw a picture to see what's going on, here's my Argand diagram. Minus 2 minus I is down there. That is z. What I'm going to do is rotate this clockwise about the origin, and I'll end up with a complex number w here, where I've rotated through pi over 2 radians, which is 90 degrees. So I've got to work out w. I'm absolutely sure there are ways of doing this without using any complex number theory, but there is an easy way of doing this by using some complex number facts. So to get from w to z, I have rotated by pi over 2 clockwise. So what that means is I have subtracted pi over 2 from its argument. When you multiply complex numbers together, you add the arguments. If you are rotating anti-clockwise, you will add on in a positive manner. If you're rotating clockwise, you'll add on in a negative manner. So what that means is you can get W by doing the original complex number Z and multiplying it by the complex number whose argument is minus pi over 2. That's what Z is going to be. That's what W is going to be. So start that. Doing this, because the modulus is 1, it doesn't stretch it at all. The argument gives you the angle of rotation. It's minus pi over 2 because we are going clockwise. And that's okay. You can do this on your calculators. Your calculator can at least help you a little bit with this. So e to the minus I pi over 2 is the same as the complex number whose modulus is 1 and whose argument is minus pi over 2, which is all I need to be in radians. Shift set up. That's minus I. So therefore, it's minus 2 minus I multiplied by minus I. If you expand the brackets, minus 2 times minus I is 2I. Minus I times minus I is plus I squared, which is minus 1. So therefore, it's minus 1 plus 2I is the complex number W. Okay, that was part A. Part B is completely unrelated. It's part A. I'm going to get rid of what I've done here. So in part B, we're looking at this picture here. We're told in our Gann diagram, A is the complex number 1 minus 2i. So this is my complex number A, 1 minus 2i. B is the complex number 3 minus I. And we are told that there is an isosceles triangle with a right angle at B, ABC, so that's a right angle. And you can also see that it's going round in a kind of a clockwise direction. It asks me to do the following. It first of all wants me to find the complex number from B to A. So finding complex numbers between points is like finding the vectors between 2 points by subtracting their position vectors. So the complex number, part 1, going from B to A is the complex number at A, if you want OA, minus the complex number at B, which is OB. So that's 1 minus 2I, take away 3 minus I. If you cut away the imaginary parts, 1 take away 3 is minus 2, minus 2I plus I is minus I. It then says write down the complex number given by BC. So I'm going to use the idea I used in just a second ago. To get from BA to BC, you are going to rotate by pi over 2 radians in an anti-clockwise direction. So I get from there to there. So sorry, in a clockwise rotating direction. So I claim that BC is BA multiplied by the complex number whose modulus is 1 and argument is minus pi over 2. Which works out that was an I. So therefore it's minus 2 minus I times by I minus I. And that's going to give me 2I plus 1 minus 1 plus 2I. We can now find the complex number at C because that's the same as saying finding the vector from O to C, which is OB plus BC. OB is the complex number at B, which is 3 minus I. Add on minus 1 plus 2I gives me a net answer of 2 plus I is the complex number at C. And we are done. Now, on this particular topic, there is no such thing as an absolutely typical question. Please have a good go at the next exercise to practice what we've done today.